Hi, this is Necklace, a humanoid robot generated by AI, living happily in a simulation world. With the help of reinforcement learning, he learned to walk. Well, to some degree. But I hit the wall very quickly when attempting to improve his walking gait, as the algorithm, the robot model and the learning objective were all too complex to comprehend in a short amount of time. As people say, sometimes you need to go backwards before you can move forward. Maybe I should try on a simplified version instead, develop some intuition on how the learning is done, and gradually build up complexity from there. Now, introducing Necklace, the self-balancing bot. It has 2 wheels, and that's about it. Sorry about the broken mesh surface, I really have no artistic skills. And hey, he falls just like his sibling Necklace the humanoid. The self-balancing Necklace is not self-balancing yet, but that's the objective, and hopefully he stands by the end of the training. Compared to humanoid walking, a self-balancing bot problem is much easier to solve. It is a classic problem in control, and that is the idea behind hoverboards and segways. A naive solution can be described in one sentence. If you think you are falling, drive in the same direction. If you accelerate faster than the speed of falling, the balancing bot stands. To make the problem really simple, I also made Necklace action discrete. And there is only 2 actions it can choose from: accelerate forward or accelerate backward. So, the one-liner logic is to move forward when it tilts forward, and vice versa. And that works. And that shakes. I wouldn't want to ride a Segway with such control, but let's call it the baseline, and see if Necklace can learn a similar behavior on its own. For learning, I am using a popular open-source reinforcement learning package called Stable Baselines 3. Its basic API is very simple: pick a learning algorithm, give it control of Necklace, and it starts learning. Necklace receives 1 point for each simulation step that he is standing, and the episode restarts from 0 after he falls. Lucky for me, it just works out of box in this binary action case. After 30 seconds of head scratching, Necklace quickly found the right way to improve. And after around 2 minutes, he passed the training by achieving the highest score possible. Necklace the balancing bot is balancing. That was easy. But the vibration is still present and Necklace is wandering around in space. I shall come back to improve these 2 aspects, but first, how did it learn? The algorithm used here is called DQN, which stands for Deep Q Network. DQN was one of the earliest work to successfully combine deep learning and reinforcement learning, and was the first to achieve superhuman skills in many Atari games. The D suggests usage of deep neural networks instead of classic tabular approaches, and the Q network indicates the algorithm learns to estimate the goodness of taking an action at a given state. An action with a higher score suggests higher future cumulative rewards, and that action should be preferred if reward maximization is the goal. But if Necklace is feeling uncertain about its own estimates, it could choose to try other actions and explore. The Q network in this case takes in the current state of Necklace, and magically outputs the score of the 2 possible actions. During training, Necklace collects experience, and updates the Q network to closely approximate the actual rewards it received. And after learning has converged, Necklace uses its Q network to estimate which action has the best score. And that action is what Necklace takes, which is shown in green in the Q value plot. While Necklace did not learn to balance itself at the very up straight position, because it was not told to, it is clear that Necklace learned to alternate between driving forward and driving backward to maintain its balance. Now it is time to address the oscillation problem. Having only 2 choices, full throttle forward or full throttle backward, it is not Necklace's fault that he is so shaky. So, let's give Necklace more choices, and see if Necklace learns to use them. I also modified the reward function by adding a penalty to discourage large swings and another penalty to make motion smoother. With the added complexity in action and reward, Necklace will need more time to train. After 1 minute, he learned how not to fall, but it took much longer time to gradually improve its reward, and thus improving smoothness. That is much better. By using only 10% of its maximum effort most of the time, and only reserve large actions for extreme cases, Necklace has managed to balance smoothly. Note how the estimated Q value of each action changes as Necklace swings over different states. For example, all Q values drop when Necklace deviates from the up straight position, telling Necklace to resist and come back. And that is right, because of the penalty I just added. Good job, Necklace the Balance Bot, you have earned your name. And I need to go back to studying, so Necklace can try another algorithm next time.